Further, we have John Tasca and his presentation. So thank you so much, John.
Okay, here we go. You hear me?
Mm-hmm.
Good. Let me get started here. And well, it's like a high school reunion. I know so many people from all these years ago. That's awesome. For those of you who don't know who I am, my name is John Tasca. Let me give you a little highlights, bullet points of my life in this industry. I'm the president and CEO of a calibration company called Technical Calibration Labs. Many years ago, I was a technical support engineer for Macbeth's lighting line back in the early 90s. I developed the original light booth calibration program for Macbeth using the spectroradiometer. I started Technical Calibration Labs calibrating color matching equipment 1994. It'll be 30 years this June I've been doing it. I was the first to be accredited in the ISO Guide 25, which is now ISO 17025 in optical radiation. And my first auditor in doing this in the light booth calibration was Dr. Yoshi Ono. Maybe Nick knows Dr. Yoshi. So he had come up to the little town of Monroe, New York, and did my accreditation for me back then. I've been one of the original members for the SAEJ 361 back in 1997, when we were discussing going from one spec and trying to basically get a standard for all OEMs doing this type of thing. I presented papers in the past for AATCC, the Detroit Color Council. I've done presentations for the Detroit Color Council. You know, it sounds like I did a lot of stuff, but it's 30 years, okay? In recent years, I've developed this LED panel called the L-Star LED conversion panel. As it states in the title, I'm here to talk about color appearance, LED daylight for color matching. But before I get started with that, one of the things I used to do when I did presentations was talk about something very critical, especially in color matching, and that's consistency. It's important to maintain consistency when we're doing color matching. Everything's got to be consistent. The only variable that we need to have is strictly the master in the sample. If we're introducing variables into that, it's going to be a problem. One of the things I've been hearing over 30 years has been this expression: why does it match on my lights and I go there and it doesn't match? And they're all calibrated. Something's inconsistent. That's all there is to it. Because the only variable needs to be what you're looking at, okay? So just briefly going through this, just as a little background, controlling ambient light, it's gotta be controlled when you're doing any type of color matching. Just to let you know, shut off all the lights in the room, shut off the lights in the light booth. If you're seeing color on that perch or inside that booth, you're mixing color. It's like mixing paint. You gotta get the light off that perch. The perch material, it's gotta be consistent. I'm sorry, Chrysler. All right, but anyway, you know, the gray perch in the background, unless you're Chrysler, then you got black. I walk into a place, I see black perch, I say, you doing work for Chrysler? But anyway, the wall colors, it's gotta be the gray. You've gotta maintain that because you gotta remove the inconsistency. I've gone into places in all my years, I've seen grayish green walls, pinkish green walls, people just, there was gray in it, and it's gotta be consistent. A light booth, a perch sitting closer to one wall than to another wall is gonna reflect more light on the sample. That's okay. But no, the one side is going to be brighter because it's going to have more reflective power on that. Obviously, you close the power. If you just came out of prison, you're still wearing a jumpsuit, got to lose the jumpsuit. That orange is going to bounce off your clothing. It's going to mix in there. Sunglasses shouldn't be a no-brainer. Years ago, I used to wear photo gray sunglasses. And in the wintertime, you go outside, those things turn as black as night. And you come inside, they start to dim, but they never get back to clear. Be aware of that you're always, that's another kind of filtering that you're doing. Light booth calibration and maintenance, very important, and I'll explain why that's important. Because a lot of lights shift in color. They shift in brightness, and we'll go through some of that. So if all these criteria are met, and we're still seeing a difference, then what's the problem? I'll tell you, it's gotta be the light source, all right? If it's not, though, if everything's controlled, the only other variable is going to be the light source. Natural daylight is the best source for color matching. That's all there is to it, all right? Average north side daylight, Jim, we were just having this discussion, partial clouds. Somewhere in the world, there was a spec that said partial clouds, the sun position. Is the sun behind you? Is it in front of you? There are no oncoming cars in the parking lot so you don't get hit while you're doing your samples. That's the best light. So, however, this is Eliana. This is Steven's daughter. She's going to be our model, okay? However, natural daylight has a lot of inconsistencies, as you can imagine. I'm from Florida, and I guarantee you 5 miles from a beautiful blue sky is a thunderstorm. It's like the end of the world. There's a lot of inconsistencies. So what we've been trying to do is come up with a way of controlling natural daylight. How do we control natural daylight? Artificial daylight. Whatever it is that we're trying to do, it needs to be consistent, as close to daylight, natural daylight, as possible. It's got to ideally contain all the spectrums, the color in the sun. You see the prism. I mean, you guys are all smart people. You know, you divide the light up, you see the entire spectrum of the sun in that prism. So we have to get as close to natural daylight as possible. The brightness has got to be similar. We can't have variations in brightness. I'm just loading my gun right now because there are things that we see in the industry all the time. Consistency in operation. You know, there can't be fluctuation. Something happens on one side of the building, it's affecting what's happening on the other end of the building. There's got to be consistency maintained from unit to unit and customer to customer. So there are a couple ways that we've come up as an industry to try to replicate what daylight is all about. D65 is our magic number. We've done it with fluorescent lamps, with tungsten filtered halogen lamps, and I'll be talking a little more about the LED situation. But before we talk about the pros and cons of each one of these types of daylight, we have to find out certain things, ways of evaluating that daylight. There are many ways of evaluating whether the daylight is acceptable for what we're trying to do. The couple ways that the industry has developed over time has been the Metameric Index, where lights are graded from A to E, and we're going to talk about these a little closer. That was developed 40 years ago. The Color Rendering Index was developed about 30 years ago. TM30, the fidelity and saturation, was developed 7 years ago. And a part of that is the color vector graphic. Just to look at these more closer, the Metameric Index, basically what it's doing is you're taking a metameric pair. How does it look under natural daylight, the sunlight, okay? Now, what do you have, Mr. So-and-so, as daylight source? You go inside the booth, which what we call daylight. Is there a shift in there? And that delta E, they assign a number. If it's less than 0.25, it's considered an A light. If it's between 0.25, 0.5, it's considered a B light. This is a system that was developed 40 years ago. Understand, it's 40 years ago, way before LEDs were even considered. This is how we did it. This is also a calculation. It's not a reading. And that's important to know. Because calculations, you could do things to achieve a certain thing. I'm not saying people do this, but because it's a calculation, you run that risk. All right, you could give something a B grade or C grade or an A grade, however you shift it. Not saying anything. I'm not presuming anything. I'm just saying it's not a reading. Okay. Again, this was when LEDs were that little red light on your VHS player that says that was on. The technology in LED wasn't there 40 years ago to even consider this type of thing. The next way of evaluating was a color rendering index. The color rendering index used 8 pastel colors. It's important to know that these are 8 pastel colors. They aren't the actual rich saturated colors. It was developed in 1930 and last updated in 1995. It was the industry's first attempt to standardize how how things appear under different light sources. It consists of typically the sun and 8 pastel colors. It would grade your light from, the color rendering could be from 0, doing color matching in the dark, to 100 being color matching under the sun. But they used these colors 30 years ago, again, way before LEDs were being even considered for anything. The next system and the last system would be the TM30, color fidelity. In 2017, the International Commission on Illumination recommended this procedure, CIE 224, for measuring and specifying color rendering properties of light sources. Abbreviated TM30 is a more comprehensive and consists of 3 parts: color fidelity, and we'll go through those parts, color gamut, and the color vector graphic, to give us a more meaningful way of determining how good this light is. So what they have done was go from 8 pastel colors to 99 real colors. Better volume, better way of comparing, how a light source is going to perform. Hold on, I don't want to get too ahead of myself. That's one thing when I was practicing, I was like 3 slides in advance. I'm like, hold on, okay, let's just take a brief thing here. When color rendering index uses 8, as I said, colors, the TM30 uses 99 colors from real world objects. Like color rendering CRI, color fidelity index goes from 0 to 100, 100 being the best setting you could get. That this is sunlight quality light. And all of these light sources that we're going to evaluate all do a comparison to natural sunlight. Also, the TM30 uses real life categories. They categorize them into 7 different areas: skin, nature, textile, paints, plastics, printed material, and color systems. So they've taken a lot of time in developing this system I need a good idea of what this light source is going to do, a better way of judging with that light source. They also use the color gamut, which is how intense is the color that we're looking at. I'm comparing this, I'm getting a visual of almost an LED value, where, what's the color, how dark, how bright it is. This gives us a better idea of the light source itself. And the last thing that we'd be talking about when it comes to the TM30 system, it does the color vector graphic. This is an example of the color vector graphic. But I have actual readings of these 3 light sources. The black line would indicate the actual sunlight, okay? The red line, that's the red circle, that's a part of that would be considered your light source. How intense is it? How saturated is that color? Obviously, things on the inside of the line would be less saturated. Anything on the outside of the line would be oversaturated. It's a visual that was developed with this TM30. Okay, and to summarize the TM30, it's the latest development in color metrics that most accurately measures the color rendition of many light sources, especially LED. Those other ways are good ways, but they were never intended to measure LEDs. There you go. Just a comparison. TM30 that was developed in 2017. That's 7 years ago. The CRI, the latest one, was last updated in 1995. Technology moves on. TM30 uses 8 real colors. The CRI uses 8 pastels. The TM30 perfect rendering compared to the sun would be 100. CRI, again, perfect rendering would be 100. TM30 uses the color gamut. How intense are these colors? Does this light produce? On the color, plus 100 plus or minus whatever it's going to be, 100 being perfect. Never considered color gamut. Color saturation with the vector graphic, CRI never considered it. TM30 takes LEDs into account, color rendering doesn't. TM30 divides it into 7 categories, nature, skin tone, etc. CRI does not. So what we're going to do is take a closer look at the 3 sources that we have for looking at our samples and how we produce artificial daylight in the industry. The first area, first one we're going to look at is fluorescent lights. It uses proprietary technology in the phosphors in light bulbs, and then they light the lamp and let it fly. There are some companies that use this technology and they have their own proprietary mixture of phosphors. Okay, so if you're buying, it could be anywhere from 3 phosphors to 9 phosphors, depending upon where you're getting the lamps from. You might be installing 7 phosphors, some guys using 3 phosphors. There's an inconsistency unless you're going to use the same type of bulb. Okay, what I'm going to do, I'm going to be using the TM30 for all the analysis for the 3 light sources that we're going to talk about. And I've used the same radiometer for the meters, so there's nothing, I went on the internet, I started looking for stuff like that. This is actual readings that I've taken for all of these. So the first one, the fluorescence, this is the power, spectral power distribution of it. From just looking at this, I'm looking at color spikes. Fluorescents are known for color spikes, all right? You could have good color temperature, you can have whatever you want to have on it, but the thing is that if you're looking at a sample and you're seeing, well, mine looks a little, I could see green in my sample. Where's that coming from? I don't see green in my, there's a color spike. You have to take that into consideration. This is something that if everybody's using the same bulb, the same fluorescence, that's fine, because we're all seeing the same thing. But if you're not seeing it and you're seeing it, there's something inconsistent. This is the TM30 and the color rendering index for this. Ideally, this far right edge over here would be 100. And that's basically a representation of what you're seeing over here based on these 15 colors that they're using to analyze. The next slide is going to be the data that was produced from this reading. Right off the bat, on these fluorescent lamps, these are bulbs right out of the box, right from the manufacturer. The color temperature is 6719 Kelvin up here. The illuminance is kind of high on it. Color rendering, 97.2, not bad. The color fidelity, 96, not bad. And the colors R1 through R15, about 84.5 to 99. That was at the far right edge of the color comparison on the TM30. So let's look at some pros and cons of fluorescence. Fluorescent bulbs are inexpensive. These fixtures are pretty cheap. You got a half dozen of them for the price of one of the other ones, okay? So they're pretty inexpensive to purchase as a light booth. It uses less electricity. We're living in a green new world. Reduce your carbon footprint. They use proprietary phosphors. So those bulbs are very good and very specific for those applications. I mean, you just can't go to Home Depot and throw in a D65 bulb. That's a very bad thing to do. You need bulbs from the manufacturers because they got proprietary phosphors in it. The cons, fluorescent fixtures and bulbs, they produce color spikes. You're going to get color pop. Good if everyone sees the same pop. Bad if only certain people see the pop. No calibration. Does not ensure that the lamps are in spec. You need to be able to know if these things are calibrated or not. They come with an hour meter to tell you when to rip out the bulbs, when not to rip out, when to replace the bulbs, that type of thing. There's a warm-up time, like a lot of bulbs, they require stability. I'm guessing around 3 minutes, and the color temperature range on that is 400 degrees Kelvin. That's not what all fluorescent manufacturers, it's based on one manufacturer that I know their name rhymes with Ekbet. okay? But it was 400 degrees Kelvin, okay? But when you're thinking of a window of 400 degrees Kelvin, if you want a bulb that's 6,500 degrees Kelvin, this goes for with any of the technologies. 400 degrees, that means you can visually see a shift from 6,500, 6,100 in spec. Women could see more cones and rods, they could see more shades of colors than guys, okay? So they might be able to detect a 400 degrees difference. But that goes plus 6,900 degrees Kelvin. So now you're looking at an 800 degree swing. You could have a bulb in your unit that's 6,100 in spec, another bulb in another unit, 6,900 degrees in spec. That's an 800 degree shift in color. You're gonna see that, even me. Okay, something to consider. The next are the filtered tungsten halogens. It's very simple how it works. It's a piece of glass and a halogen bulb. That's how it started, a long time ago. And the idea was to convert your halogen bulb of about 2,900 degrees Kelvin up to 6,500 degrees Kelvin. So what they do is they slap a piece of blue tempered glass in front of it to get that conversion. Let's take a look at this data. This is the spectral distribution of a tungsten filtered halogen lamp. Again, all the same meter, all the same fixture. It's got a bit of a spike and a bit of a dip. Again, this far edge over here will be perfect sunlight. All right, and and I have the reading on the next page. It's about, the highest point is 98.4. I don't know if you can see it back there. The lowest point would be the red, would be 73.5. Again, we got just being consistent across the board. Now we're going to look at some of the data sheet for this. 6502 was the reading taken on this tungsten filtered halogen fixture. Let's see. The illuminance, 105-foot candles on the low side, but still in spec. Oh, we're going to talk about that. Color rendering index, 94. Again, that's pretty good. Color fidelity, 95. Pretty good. Colors R1 through R15 is as low as 73.5 and as high as 98.4. And we'll look at the pros and cons of this. It's been an industry standard for 50 years. That's all there is to it. This is what we use. This is all we got. This is what we use. Industry standard for 50 years. It's got a nice smooth sinusoidal, not a lot of popping going on. Calibration is available and highly recommended. Not because I'm in the business, but because you gotta do it. There's a reason you gotta do it, and I'll explain it to you. The cons, high power consumption. Tremendously high power consumption. I have a halogen bulb in my driveway years ago in Monroe, a 150 watt halogen bulb. I could light up the entire driveway, 200-foot driveway. Stephen will tell you, we went sleigh riding down a driveway. Lit up the whole driveway. This little box, most of the lights, it's changed a little bit, has two 750 watt bulbs. That's 1,500 watts in that little box. They've reduced it to two 500 watt bulbs on some of the newer units, which is about 1,000 watts. That's a lot of power. That's a lot of electricity. It's a lot of heat. You know for yourselves on some of these units that after 2 minutes of operations, blink, it goes to cool white. Because it's too hot. It's saying, let's cool this thing down. It's old technology. Halogen lamps change color with repeated use. These halogen lamps, like any other filament, as they burn, they have a certain color. We saw 2,900 degrees Kelvin. The problem with them is as they get older, the filaments get thinner. As they get thinner, they move further away from the red spectrum because they start to burn whiter. So the color temperature starts to go up. That's why they got to be calibrated. You got to bring it back down into the red spectrum That's why calibration is high. You have to do it. People, I don't need, yeah, you gotta do it, because these filaments are getting brighter, they're getting wider, and the more the blue filter is coming through. So we gotta get it back down with more red spectrum. Inconsistent unity in the brightness. SAJ 361 says it's gotta be between 100 and 160 foot candles. That basically says, tell me the numbers, put them in there. You could drive a truck through that spec. It's too large of a spec. But it's kind of like, well, what are we using today? Well, we're using this unit over here. Okay, what's the range of it? And I'm going to show you the range of it. This has got to be tighter, because I guarantee you all the calibrations I've done over the past 30 years, I've gone in facilities and it's kind of like, why isn't anybody using this side? Well, I can see colors better on this side. Why? It's brighter. This side is dimmer, but they're both 6,500 degrees Kelvin. That spec is way too wide, but that's all we have. That's all we have to work with. That's something to consider. With the filtered tungsten halogen, you should warm those up also. When we do our calibrations, we let it stabilize for about 3-4 minutes before we start taking readings. Of the three, it's got the lowest CRI of all three sources. It's not bad. It's just a number right now. Factually, it's the lowest of the three. Doesn't make it good, doesn't make it bad. All three sources have a great CRI. Lamp availability is becoming increasingly difficult. And before we talk about trying to find bulbs to put in these things, what I'd like to talk about, let me just look at the next slide. I want to talk about the brightness of these filtered tungsten halogen units that are in the field nowadays. Back in 1994, when I started the business, the Troy Council Bulletin number 3 said the brightness should be between 90 and 120 foot candles. You know where we are right now. DCC says should be between 125. Now, SAJ 361 says between 100 and 160. Get the truck, you're going right through that spec. It's like nobody fails. Everybody passes. It's just too wide when we're doing color matching. We all have to have the same difference. And the reason for the difference is the blue glass. That's all there is to it. The blue glass is, I don't know how it's done now. I know how it was done 30, 35 years ago. They're made in certain melts, for a certain quantity of melts. Let's say 200 pieces at a time. It's like anything else in the industry when you have the lots. Oh, what lot number is that? Okay, and the calibration would actually make the adjustment. Oh, okay, we have the new glass in there. We need to bring it up because we need it to be 6,500 degrees. So all of a sudden you start cranking up the power supply, they get brighter. The next lot is a little bluer, a little deeper blue. Oh, it's too, we gotta bring it down. So now it becomes dimmer. You got it, that glass that hasn't been controlled. It's just blue glass. Many years ago, I've had the glass sent to a lab out in Arizona just to measure it because I was wondering what it was all about. And you know what they told me after doing all this scientific analysis? They said it's blue glass. There was nothing specific. It converts. That's what it's supposed to do. But it's not controlled as to how blue it is. That's what the calibration is all about. And I think it's gone kind of like a bit awry, so to speak. Over the past 2 years, I've been going to doing my calibrations, and the next slide is going to be the results of that. All right? And this is done in brightness order, or foot candles order. You can see in the grays is 6,500, 6,501. These are my calibrated readings. 6,503, blah, 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 up to 6,500. Starting as low as 88 foot candles, and as high as 160 foot candles, 162 foot candles. That is very, very wide. And we've seen it brighter than that on a brand new unit at 186 foot candles. It's 6,500 Kelvin. I guess it's good. It's not good. Because now you're going to see things that somebody that's under a light that uses a 102 foot candle is not seeing, because you're dumping more light onto your sample. there's not enough consistency in this window. If we reduce this window back to the original spec being 120-foot candles, or 125-foot candles, half of these units would fail. But guess what? They're all passing now. Not good. Consider that when you're looking at it. And right now, I mean, I know there's another way of doing it. With the newer unit, I don't know, brand new units, but I mean, a previous generation that we're at right now, there you can attenuate down. They put these screens in there to make it dimmer. But what happens if you don't want to make it dimmer? You want to make it brighter? You can't make it brighter. You can only make it dimmer. Years ago, see, I'm like an old timer now because I've been doing it for 30 years. The old Macbeth lights used to have a big black knob in the front of it. I don't know if any of you remembered it, because the first ones that were manufactured would be like, oh, you want it brighter? Turn up that variac, you're cranking it up. Ooh, I can really see color now. Color went all over the place because they were making the filaments whiter. So finally, we got in there, we're like, no, you can't be touching that thing. But there was a big knob on the front of it, you just said, make it brighter. We didn't understand what we were doing back then. They eliminated that. Now all the adjustments on the power supply are internal. But that's what's being used right now. And are these basically attenuating filters. And the last thing I want to talk about regarding this is the availability. It's no, go to Lowe's, go to Home Depot, try to find something with a filament in it. It doesn't, it's getting increasingly difficult. I mean, this is USA Today. You can't manufacture or even sell things. The ban started in 2023, and they're predicting by 2025 that would include compact fluorescent lamps will be phased out under the Biden administration. New standard. These are being phased out in favor of LED lights. It's a green new world. That's all there is to it. Right? Everything reducing of carbon footprint. That's what it is. So with the amount of energy these things are being sucked out of the building, out of everything, we're not allowed to even buy them anymore. I don't know how you feel about it. I got my problems with Big Brother, but it's okay. I'm not going to go there. Okay. USA Today is basically says the same thing. You can no longer purchase these lamps or be manufactured in the United States. This also applies to halogen bulbs, and it's possible by 2025 that would go to fluorescents. They're being phased out in favor of LEDs. Here's one. If you guys don't know, but I'm an Apollo geek. This Fred Hayes, Apollo 13. I thought this was a good slide. And Gene Cranston, you know that guy, right? All right. Detroit, we got a problem. What about LEDs? Let's take a look at these now. Are you ready for this one? There's Eliana, that's Stephen's daughter. Now that's a good idea, right? She's a sweetheart, let me tell you that. I'm a lucky guy. Evaluating LEDs for color evaluation. The TM30 was a system of evaluating light, specifically with LEDs in mind. In developing this new method, thousands of LEDs. These aren't LEDs from years ago. These are different LEDs. LEDs were analyzed. The number of samples increased from 8 to 99. We know that. It should be noticed that the metameric index and the color rendering index was developed 40 years ago when LEDs weren't even being considered. SAJ 361 states that LEDs may be used if they meet the spectral qualities and the luminance characteristics of, let's see, the ASTM says LEDs may be used as daylight simulators provided they meet the spectral qualities as specified. And the DCC says, made a statement that for more than 50 years, labs around the world have been using the same lighting conditions as well as standardized samples for evaluating textile appearances. They have now a committee called the RA36 committee that are looking at LEDs. Labs that needed new lights and replacement sources for color evaluation will now have a new, less expensive and more environmental friendly ways of doing color matching, and again, that was with LEDs. The bottom line is that LEDs are here, and they're here to stay. We use them everywhere. I'm not telling you anything new. Look at your street lights, look at your car headlights, look at your directional signals. I tried to look at medical, marketing, Times Square, look at Times Square, they're all LEDs. Not that we're going to Times Square. Spectrophotometers now use LEDs to illuminate the sphere. All LEDs in achieving the colors we're looking to achieve. Light boosts. Companies that are out there are producing light boosts with LEDs as a part of daylight. And what's on the market nowadays? When it comes to LEDs, I've done some research. There are a couple of these LED light boosts, but it's important to know it's not just D65 daylight, they're tunable or calibratable. They're not just 65, I don't know what it is. They could be adjusted to whatever, to be calibrated. Very wide one's about $10,700, so take all of those units, throw them out and buy these things. Dow's Light's about $10,500, and just normal, which is about $12,000, and that's just for a single light booth, single calibratable light booth. But now, we'll talk about is the L-Star. This is the latest innovation in LED technology for the light booths, and we're going to go through the data of these. It replaces the daylight halogen lamps and blue glass filters in your existing light booths. There you go. It's a patented system that does just that. Now you say, well, how good could it be? I know LEDs, I could buy them all over the place. We're gonna put up some data. But before we put up the data, I wanted to tell you something about the LEDs being used here. They're called absolute 99 LEDs. LEDs had a tendency of having a cyan gap. And some of them have this blue overshoot. The LEDs, which were a problem when it came to color evaluation, not even color evaluation because they weren't even in there, but when you took a spectral output of them, you had this spike. The traditional LED, now here comes the geek stuff. The traditional LEDs use 455 nanometer blue dye as the underlying light source and a dual phosphorus mix of green and red phosphors to achieve a semi-full spectrum. The LEDs used in the L-Star are absolute LEDs. They utilize a different method of producing white light to eliminate the cyan gap and a blue overshoot by shifting the underlying layer to 420 nanometers for a fuller, wider spectrum. And all that energy in that was moved further out to the near UV range. It's not here anymore. It's way out over here. So that's how these LEDs were developed with that. And just to look a little bit closer of these, the Absolute series LEDs have a 99 color rendering index. That means these LEDs are virtually indistinguishable from natural daylight. Oh yeah. This is your spectral data output. Again, that cyan gap has been greatly reduced. The blue overshoot has been shifted out to the near UV sector. When we're looking at these, this leading edge should be 100, that's natural daylight. And we're going to do a comparison from what the industry standard is right now to what these LEDs are right now. And looking at the data sheet for this, 6501 Kelvin, illuminance 130, right in the middle of the spectrum. Wasn't 100, wasn't 160, smack in the middle. Color rendering index is 99, 100 being sunlight. Color fidelity, 99, 100 being sunlight. Colors R1 through R15, the lowest being 96, the highest being 99.8. of those 15 color analysts we were using. These are the pros and cons of the L-Star. It's got the highest color rendition of any of the three sources. Got color fidelity, the highest of all three sources. It can be calibrated to precision. This is a calibratable source once it's inside the unit. Brightness is set between 120 and 130 foot candles, period. That's all there is to it. That is the tightest in the industry, the tightest the industry's ever seen. It's got low wattage consumption, very low. It shifts less than 30% in 50,000 hours, almost 6 years before you see a 30% shift in the LED. Where a lot of the current technology, this is all we've ever had, is shifting all the time. Brightness is shifting, color is shifting. This shifts 30% in 7 years. There'll be calibration way before that shift even takes place. No dedicated line source needed. You know, some of these units have to be plugged in. You can't be plugging it in where you have a compressor on the other side of the building kicking in, because what happens? Weak line problem. Well, better yet, I gotta call John. I don't know, I keep pressing the daylight button, it doesn't come on. What do I do? What do I tell you to do? Shut down the unit, count to 5, turn it back on again. Next thing you know it, you're back in business. It doesn't need a dedicated line source, because you're not drawing 1,500 watts, you're drawing 20 watts. Retrofit units previously deemed obsolete, Jody. Okay? And the last thing we're going to do is we're going to look at the color vector graphic of all three. This is the fluorescence. I don't know if you can see it from back there, the black being the natural sunlight, and the red being the color vector graphic for fluorescence. You can see there's undersaturation because the red's really on the inside of it. This is the filtered tungsten halogen. It's a little better. You know, certain areas are right on the line. And here's the daylight, the L-Star, it's practically on top of the entire line. So it's got the best saturation of all three sources that we're dealing with. And this is just a comparison of the numbers that you saw below, just to give you an idea, all right? Color rendering index, 94 versus 97. The L-Star is 99. Color fidelity, 95. These are all good numbers, by the way. I'm not saying they're bad numbers. These are all good numbers. But if we're going to do something consistent while we're taking a step into the future where we should be, not 40-year technology, this is the way we should be going. Color fidelity being 95, color fidelity fluorescence 96, color fidelity is 99. These are not made, these are readings. R1 through R15 as low as 73.5 to 98, and as high as 96 to 99.8. And comparing it with the industry standard right now, filtered tungsten halogen, you could just look at the edges of the 15 colors of the TM30 versus over here. These are readings. These aren't calculations. These are actual readings of this L-Star technology. And these are just little side advantages. I found out what you guys are paying for electricity in Detroit. Okay, if you're going to be using just one light booth, you're going to be paying about $716 a year in electricity. If you've got 2, if you have 10, okay, you do the math. In the L-Star, you're doing $5.55 a year per light booth. You see, it's an energy saving, all right? With the halogen, color shifts with usage. Again, the filming, every time you flip it on and off, it gets thinner and thinner and thinner. In Fort Myers, Florida, they have a light bulb from Thomas Edison. It's still burning. You know why? Because the voltage is really down, and they don't turn it on and off. They keep it. Oh, it's 100 years old. Yeah. These things are well 100 years old. You dim them way down, okay? But they shift in color with usage. There's no shift. Well, better yet, there's 20 Kelvin in 5 years. But I'll be calibrating it a lot sooner than that. There's a warm-up time between 1 to 3 minutes. There's no warm-up time with LEDs. Bang, you're in color. Bang, you turn it off. Hey, come on in. You want to see it? Bang, you're back in color. There's no warm-up time. Output varies with line voltage. The big black knob. Going inside, making an adjustment. Weak line voltage problem. Okay, there's no effect. Line voltage has no effect on color whatsoever. Light degradation with flipping switches. There's no light degradation with flipping switches. It's just rock solid. Now, I'm just going to throw this out there because I had a slide, and I needed to fill up a slide. This is the old power supply. Forgive me, it's a very old power supply for the units that are out there. This technology is still being used today. Same technology. It's put in different places, transformers in the back. It's the same technology. It's just supplying voltage to a light bulb and basically controlling the input voltage. So when they turn on a compressor, the line voltage goes like this. You need something to bring it back to where it was calibrated. So it's kind of like, Captain, I need more power. Okay, they start cranking this thing back up to get it to where it should be. And then all of a sudden, everyone goes home and all the plant electricity starts going up, and then the power supply brings it down. This is the only power supply I had in my office, so I took a picture of it. But the thing is, it's the same technology. This is the LED driver. 120 volts. It operates anywhere from 110, 140, doesn't matter what it does. It still has a steady output that does not affect the operation, the color, or the output of the LEDs. Let's see. Now you're saying, are there any concerns for installing this in the unit? Is it safe to install an existing light boost? Yes. There's nothing unsafe about 12 volts. These units, you draw a half amp. The steady state of the units out there right now draw steady 12 amps. That's going to make a spark. Will it interfere with the operation of other lamp settings? No. It's an independent circuit. I'm just kind of like heading off. People are going to say, oh, you're going to mess up the unit. It's going to make it. No, it has no effect on what you have right now by installing this. Does it require a dedicated line source? No. Plug it in anywhere. It doesn't require a dedicated line source. Is there a warm-up time? We said no. Turn it on, you got 65, turn it off. Turn it on, it's got 65, turn it off. There's no effect on switch operation or warm-up time. Can the conversion be done on site? Yes. It takes about 10 minutes to put them in. I know what you're thinking, and let me see. I know what you're thinking. Can it get any better than this? John, you gotta be kidding me. Could it get any better than this? Eliana would say, yes, it can. Okay? You can repurpose your old light boost on a loading dock. It's sitting on a pallet. I've gotten phone, what do I do with this thing? I don't know what to tell you. You can't get parts for it anymore. They don't do it. You can't get them anyway. That's why I still have that old power supply. One day I'm thinking of putting it in somebody's unit. But anyway, with this, it doesn't matter. You could have the old things on a loading dock, and you're going to put this new panel in it. It doesn't need the old filters, doesn't need the old power supply, it doesn't need those 1500 watt LED, halogen lamps. It's a half amp conversion. You pop it in there, clean it up. You should paint the inside of these things every now and then. But other than that, it's going to give you color like a brand new unit. And now you're wondering, what's this going to set me back? What's the price on this thing? This is installation, calibration, ISO certification, a real certification where you're getting numbers, you're getting before and after readings, not just a certificate saying it meets certain specs. These are actual readings like you've seen on my certificates. They're about $1,500, and for your DCC members, for a limited time only, it's going to be about $1,200 installed per unit. And we're working on a couple of things in the future. The L-Star tube will replace fluorescent daylights, 24-inch and 48-inch light fixtures, and they will be calibratable. so you can get data on them. The color harmony room fixtures, Chris, we talked a little bit about that. These will be able to go into fixtures, and they just aren't going to be, 2x4s sitting in the ceiling. These are going to be calibratable fixtures. And the last thing we're working on is software to remotely calibrate them. Would actually say eventually, that's a little bit down the line. I'm getting a bit ahead of myself, but I'm already starting to think of ways of using this technology that would be cost savings all across the board, because now we're in this world where you can use the internet to do certain things, to calibrate certain things. So that's it, and I gotta put my last picture of Eliana up. Come on, are you kidding me? Are you kidding me? Is she a kid? Steven makes beautiful babies, doesn't he? Anyway, I'm gonna be passing out some business cards. Some of the business cards have my old address, sorry, Bill, and some of them, but all the information is on the same. And if you did this QR code, it would take me directly to the website. There's a section that's called L-Star, and it'll give you information about it. But that's it. Thanks for coming. I appreciate it.
You can still switch to cool white and
Yes.
horizon.
All of those settings will not be affected at all. It only is regarding daylight. Yes, sir.
Light burnout like we have right now in our police bars, replacing bulbs, I mean, taking it light, is this going to be all value?
There will be no, when it comes to, there'll be no halogens in your units anymore. There would be these LEDs. If you ever had that desire to burn electricity, they could easily be converted back. But right now, there is no, that will have no effect on it whatsoever. It's independent. It's just 120 volts connected to the driver. And once you got it connected to the driver, you're flying. You're flying. I'm going to, very optimistic to say 7 years, but this is data accumulated from this new LED technology.
Yeah, we have like 6 sources. Like we just talking about D65 changing to LED. Do we have a plan? Like you mentioned, like by 2025 CFLs would be gone. So like on the U30, is there any plan that will also go LED?
Yes. Now, my plan to do it is based on 6,500 Kelvin, but these absolute 99 LEDs have the ability, they have color temperature ranges as low as 2,500 Kelvin, which could be adjusted, all right? They've got 30K LEDs. Again, that's a part of these L-Star panels. And the way this technology works is that there are D65 LED strips, and then there are 2 U30 strips. Okay, so you can increase that U30 to bring the daylight down, or you could basically eliminate it to bring the 65 back up again. So it's calibratable. So to answer your question, will there be LEDs for things like U30? Yes, it already exists. It's just not in a tube form. That's what we're working on for 24-inch and 48-inch fluorescent replacement tubes.
So this would replace, like, we don't need CFLs in future once we do that.
That's correct.
Okay, so the booth would have all light sources with LEDs.
Yes. Yes, and the thing is that it's very difficult to be getting these halogens. I'm pretty sure, I don't know where I read it, same like you, I read things, I'm like, I don't know where I saw it, but I'm pretty sure that right now one of the light booth manufacturers are having a difficult time finding these light sources, so they're obsoleting certain units because they can't get those bulbs. It's already happening. All right, so LEDs are where everybody's going to be going if they haven't gone there yet, which I'm assuming some of the manufacturers should be looking at this by now. If not, they're going to be way behind the curve. But that's about it. Go ahead, Bill.
John, what are the auto companies doing? Are they getting converted over?
This is my first intro to it. I don't know. I'm assuming that, I have to assume yes, as a calibration guy and a businessman, that's the way that they're gonna wanna go. I'm not quite sure what they're doing about it themselves, but if they haven't, they have to go in that direction. And that's why I'm here to introduce this.
These are global, China, Europe?
Yes, they're as global as the driver is global. So the driver itself, it's basically, if it's a driver that operates on 110 volts, the output's gonna be 12 volts DC anyway. If the input's gonna be 120 volts like Europe, output's gonna be 12 volts DC anyway. And that's just a replacement of the driver for that application or that country. So yes. Yes.
So are you working with the standards groups to try to get these LED incorporated more into the standards?
I haven't been working with the standards organizations. I just found out the stuff that DCC is doing about their research in it. I haven't reached out to them. That is something that would be exciting to get their part in. I think they're working with Verivide in their light booth to do analysis of the LEDs, whatever LEDs that they're using in theirs. That's the only thing I know. Yes?
Do you have any of the light booths so we can see a visual comparison of the LED versus the
That's a great thing. The answer is not here. Not here. It was a matter of, shipping a light booth in from it. I was actually thinking, what customer that I have I could borrow a light booth from. But I will be looking into doing at one of these trade shows with automotive and get two light booths, because I have a couple light booths in my office. Get one with both situations, or better yet, in your particular applications, just to, let's say, accelerate it. If you said, can I get a demonstration? I've done that at BASF. I've done that at a couple companies where I put them in and said, hold on to them for a week, for a month. Let me know what you think. So you could do your own comparison, especially if you have 2 units or 2 separate areas where you could do an evaluation on your own. I know we've done some color matching at General Motors. We've done at a couple of the locations, just because it was a big enough area where we could get enough people around the perch to see what the differences are. And I think there was a pretty favorable response to that. Tacos for lunch, huh? Come on. The DCC do good or what? Go ahead.
What's the flicker rate on that switch mode power supplies versus the old school ones, which are nice flat, reflect video?
0.003. They're virtually undetectable.
Nothing like video. I think video. Before that starts to become a.
Yep, no.
It's one thing, it's when you start doing video.
No. Yeah, absolutely. And these LEDs in here they're called photograde. Not photograde. Like they were originally produced for that application. Okay, so I've taken them into a different application of color matching because of the outputs of these things that's just so amazing. But they were actually produced for video and sets like that. Anything? Terry? You done? Oh, no. Did I answer your question?
I think you did. I'm hearing 120 to 130 foot candles. That's much better than 100.
Yeah, that's a very, very, very wide spec. And it never was intended to be that wide. You could see the original specs for only like a 30 foot candle window. These things are going to be about a 10-foot candle window, really, really tight. So what you see here, you should see there. That's the idea. Eliminate that as a variable. Good? Well, thank you all for coming. I appreciate your time. It's scanned, just get your thing, you can always www.lightboothcal.com. All right? Anyway, thank you very much again. Oh, sweet.
Your honorary secret word.
Hey, it's like the Oscars. Hey, check it out. Thanks for that.
Thank you so much.
Oh, you're very welcome. Thank you.
Good job.